Yo. So we're finishing up, or picking up where we left off, rather, on the physics of AI, right after the mathematics of AI. So we're going to go over time, velocity, acceleration, and trajectories. So a lot of physics concepts that, if you've taken any physics courses, you should be very familiar with, but the kind of recontextualizing them specifically with Unity, which is kind of what I'm hoping for, because it feels like this might end up being something we end up skipping through and being like, yeah, I know, but maybe there's more to it, so we're going to give it a shot, but definitely calculating trajectories is going to be something new, I think. That's like the one that I'm for sure on, like, that's going to be new. The rest of them, we'll see. So starting off with time, we're probably just going to go right into it, unless you had anything to say.
No.
Because I don't have anything to show. I didn't change anything since last stream. All I did was delete all the duplicates of Jerry, so there's only one. Okay. I'm going to put her in 1.5.
Time is an essential measure in physics systems, and until the late 1960s, it was defined in terms of the Earth's rotational spin. But since the Earth has been slowing down ever so slightly every year, this baseline is no longer accurate enough for scientists. Today, time measured in seconds is based on the duration of rotation of a radioactive atom. Time is a fundamental mechanic used in games. It's not only presented to the player for challenges, but it's also used for everything from moving objects, calculating physics, synchronizing networks, and writing shaders. With respect to artificial intelligence programming, time is used to move characters around an environment and synchronize movements, transitions, and align them with animations.
I feel like is she too fast?
In all physics calculations.
Do you want me to slow her down?
We're going to have a look at how
I feel like she was.
In particular.
Was that just one step up?
Well, I had her on 1.5.
Oh.
I could just put her on 1x though if you want.
No, it's maybe 1.25. I think that's the one I
work with time and the different types of time that there are.
No, that's too slow.
Time in a computer game
Never mind, you can do
numerous sources. Of course, there's the computer's own clock.
You can do whatever you
want.
want.
There's the engine itself, which also runs cycles that aren't based on real time, but on the processing power of your computer. You'll be familiar with Unity's update method. This runs once per frame. How fast it takes to run depends on your hardware, operating system, and the load already on your computer. If you try and use update as the basis for real time in a game, then your game will run at different speeds on different computers. Unity also has a late update method. This runs once per frame as well, but after the animation updates. Then there's the fixed update. This occurs in the physics cycle, and it may run more than once per frame. And last but not least, there's the graphical user interface loop. It may also run multiple times per frame. Of course, there's a whole lot more going on between these loops, and there's great documentation in the Unity manual that illustrates it. It's really worth having a look at. But what we're most interested in for working with our AI are the fixed update, the update, and the late update. Which one of these you use will depend on what you are trying to achieve, but my goal in this lecture is to examine the different speeds at which they run and to devise a way for moving an AI in real time. So to investigate each of these different loops, what I'd like you to do is create a new Unity project and bring in the starter file that's attached with this video. When you open up the time scene that's in it, you're going to find 4 versions of the Atom model from Unity. Now at this point, if we press play, all they're going to do is just walk on the spot. So they're just playing their own walk animation that is on the character. Okay, so over in the hierarchy, you can see each...
I might need to replace Jerry with Fridge Guy so I can actually have a walk animation, because I don't have any animations for Jerry. Do you want me to send you Fridge Guy and like a walk animation or something, or you want to just download something from Mixamo? It seems like we might need that.
I don't know. I might just download her project if we're gonna.
I guess we'll see how much it really matters.
Yeah, I feel like we maybe should just watch for a little bit to see. I think the way we did it last time was good.
Just watch it the first time and then come back and then try to implement it?
Yeah.
That's probably smart, yeah. Okay.
I've been working all day on Unity as well. So
okay.
I'd be happy
to
just watch some tutorials.
Of these 4 atoms, and they're all named something different. The update atom, if you click on him, you'll find that it has the update move script attached to it. Late atom has a late update move, fixed atom has the fixed update move, and seconds atom has a seconds update, which we'll get to in a moment. First of all, let's have a look at the update move script that's attached to the first atom, which is the one down at the bottom of the scene. So in the scripts, if we open up the update move, you'll find that there's just the basic update loop in there and no code whatsoever. What we're going to do is just translate our character along its z-axis, which is its forward direction, with each update loop. So we will put in a this.transform.translate 0, 0, and then 0.1f in the z direction. Okay, so we've got that. Just save it. Now let's switch back into Unity and press play. And we'll now see that our update atom actually moves forward. Okay, so we've got him moving forward. Let's go back into there. I'm actually going to slow that down just a little bit more by making that 0.01. Otherwise, we won't see any effects before they go off the screen. Okay, so we've got that line. Save it. Now, what I want you to do with it is just grab a copy of that line. Then what we're going to do is go into each of the scripts, not the seconds update, just fixed update. Put that script in there to move on a fixed update. Save it. Go back to Unity, open up the late update, and put that script in there and save it. Now, what we're going to find is that each atom is going to be moved in the z direction by 0.01 each time these particular loops run. And that'll give us an idea of how quickly they're running. So let's press play. Okay, so our seconds atom in the top, we haven't done anything with him, so we won't worry about it. Now we've got the update atom, which is down the bottom here. He seems to be kind of gaining on this guy back here. Now this guy back here is our fixed update atom. The update atom and the late update atom, now because of the camera view, they've kind of got out of sync, but they're actually still right on top of each other. If we just maybe find one over here and just zoom out, there you go. You can see these two guys in the front.
Sorry, what does she change? What does she change with these? I was
It's just
distracted.
different update methods. So they're all just moving along one axis at the same rate, basically, but one's in update, one's in late update, one's in fixed update.
Yeah.
And it looks like the late update was the slowest one. I'm not fully sure which one it was that she highlighted. I think it was the fixed update, because she has it highlighted right now.
Yeah.
So the fixed update
that would make sense.
is the one that's the slowest.
Late update would just be one step behind
Normal
update.
Yeah, because she said fixed update can run multiple times.
Yeah, it's independent.
Okay.
They're still on
And
par
what's
with
the
each-
last one? Was that the
She
GUI?
hasn't done anything with him yet.
Oh, okay.
She called him seconds atom. I don't really know what that means. It's like a new method that uses seconds, I guess.
Oh, okay.
She hasn't gone into it yet, though, yeah. She said don't worry about him.
I made myself a mod.
A mod? Oh, in the
Yeah.
Twitch chat?
Yeah, that was my distraction.
Cool, okay. And yeah,
now
it
I
shouldn't be
have-
followers only chat anymore.
Oh,
People
I
should
have a
be...
sword.
You have a sword? What? What's going on?
I have a
Is that
sword.
what being a mod is? They give you a sword?
Look.
Whoa.
Oh, I feel so powerful. Nobody better come in this chat or I'll strike them down.
Now that we're not in followers only chat, some guy's just like, hey, I've been watching these streams for a while, but I couldn't because I'm afraid to follow, and bam. All right.
You want engagement?
Ban.
Because their update loops, the update and the fixed update, both run once per frame. So they're getting the same amount of Z translation each. Now, the fixed update atom, which is this guy back here, he's a bit slower. The fixed update runs as often as it needs to update anything that's going on with the physics system. In this scene, there's really no physics going on whatsoever. So therefore, it's actually running every now and then, and not as often as each particular frame is, as we can see here. Now, what does it mean that these characters are moving at 0.01 per frame? Well, not a lot really. It just means that you can see the frames per second embodied in how fast they're walking. So if I ran this same thing on a much slower, older computer, then it wouldn't keep up with the speed that these are going, because the update on that particular machine is not going to run as fast. You're going to get a slower lot of frames per second. So this kind of thing with the time doesn't work very well with game characters if you want consistent performance across all of the different platforms that you want to deliver it on. So what we're going to do now is we're going to go into the seconds update code
iPhone.
and actually move the
What?
character based on seconds.
iPhone.
iPhone?
Yeah. She said all the different platforms. So I said iPhone.
Well, this is reminding me of how in Unreal it was like discouraged to use the event tick.
Yeah.
So it's probably the same idea, but just for like certain things.
We have an event tick as well, don't we?
Well, update is essentially event tick, isn't it?
But we have like the event system
Oh, I guess that's
as well.
true. I don't know if that's the same thing. Maybe there is a separate event that would just fire constantly like that, but I guess you would just put it in update. I don't know. But yeah, either way, it just
It is very similar to
I
update, though.
remember that like being a problem.
Yeah.
So it makes sense here. That's smart. So I'm curious what seconds update is going to be. That'll be helpful, I guess.
It'll probably just fire every second, I imagine.
Or where does it get that? Like, I guess we'll find out. But like, I wonder
Yeah.
if it accesses like the computer's
Time.
internal clock or something.
I think it's just time delta time.
Oh, okay. Oh yeah, I guess
But we'll
that we've
see.
already been doing that, huh?
Yeah, because that's
So
the
when
amount of
time
time
is-
between each frame.
Used in physics calculation, it's based on meters per second that you're moving things. If we actually use the real time, the real world time to move the character, then we know that it doesn't matter which computer you put it on, you're going to have the character moving at exactly the same rate. Now, what I'm about to do is not what you do to get your characters to move at the same rate. Rather, we're trying to force the fact of the clock seconds on your computer and use those to change the Z value of the character instead, so that we actually know that we're moving in meters per
Oh,
second.
maybe she
or in
doesn't do
however
it.
much per second exactly, rather than relying on what Unity does. And we will look at what Unity does in a moment.
Oh,
which
so I
makes life
bet
a
you
hell of a
what
lot easier.
Unity
But
does is time.delta time, and she's
Yeah.
finding some weird around like roundabout system like she normally does first, and then she'll.
We did this. We did this for the basics, the clock,
Oh yeah. Okay.
where you like get the time scale based on how much time has passed each frame.
But it will
Maybe
help
that's
you to
what it'll
understand
be.
the rate of change for these movements. So what we're going to do first of all is have a time start offset. And we're going to set that to 0 to start with. And then we want to have a bool called got start time equals false. We want to get the time that this update loop starts to run. We're going to use the elapsed number of seconds to change the Z position of Adam. Now, by the time this update loop runs for the first time, a number of seconds have gone by, and we don't want him to sort of jump right ahead of everybody else, which is why I'm just sort of putting this little bit of a fudge factor at the beginning. So we're going to grab the very first time that this happens by putting in this little if statement with a bool, which will just ensure it runs once. So time start offset equals time dot real time since startup, which is in seconds, and then we will set got start time to equal
Okay.
true, like that. Okay, now we're going to set the transform dot position. So we're basically
is good
just
to
setting
know.
the Z value of Adam based on the elapsed number of seconds. So new vector 3, and we want to keep the x and the y the same, so it'll just be this dot transform dot x, this dot transform dot y, and then for the Z value it'll be time dot real time since startup, and we'll just minus that time offset that we grabbed before, start offset. And if you really want to see what this time start offset is doing, then you could just comment this out so that it doesn't do anything. Okay, so let's put a bracket on the end of that.
I guess I'm a little lost on that. Do you think that's something we should try to talk about now, or should we just let her go and? Cause I
Yeah,
don't
maybe
know what
just run
she's
it
talking
back.
about.
Have her go slower.
Well, I just don't know what real time since startup is, and I don't think she explained that.
She just said it returns seconds since you started the script.
So our position is equal to the time since it started minus the time since it started. I guess it's minus time start offset, but time start offset is just equal to the same thing. So I guess it's just how long.
It's only
that one time.
Yeah, because it does if got start time. It starts at false, so it runs that first if, and then it sets it to true. So it's saying how much time does the first update take?
And then every further step is like
Doesn't add it.
subtracting that offset.
Yeah,
Okay.
so that we're not one frame behind. This is
Yeah,
something
we're
I
not
noticed doing the line renderer thing.
There's like a frame delay or something.
when I was like moving to the left or right, I would always see it like right behind me. And ideally it would be in front. We did something like that in the movement script.
Okay.
I think that might have to do with this as well.
Values, and of course I've missed out a position. In there, let's put that in. Okay, so let's save that. Now, when we go back into here and run it, Adam that's right on the end, so our seconds Adam, this guy over here, we know he's actually running or moving according to the seconds on the computer's clock, which will be the seconds in the real world, so like real world time. Okay, so let's press play and we'll see that he's now moving. No, so he's actually going to be moving at some rate of meters per second, whereas these guys, they're not. They're working on some rate of the frames per second or the update that's going on. So their measurements aren't particularly accurate and you'll find won't be across machines, whereas this guy, who keeps going out of frame, is going to be very consistent. So what does that mean that we do? Well, we need to know what this kind of rate of the update methods are. And Unity has a very nice way of doing that. So let's go back into our update. What we can do instead of some particular value here is we can use time.delta time. And that is the time that has elapsed between updates, and it's therefore based on a rate from the real world clock. So now that we have our update moved, we've put this into, just save that, and let's go back and play it. This time we'll be looking
probably
at
skip forward a little bit.
That is...
She's going to multiply it by speed.
Our real world. These guys are instead in here, so...
And she's just going to put it in all of them now, huh?
Actually, sorry, I shouldn't have said that, because now I don't understand what this test is.
Okay, so the moral of this story, I guess, is that we didn't really do anything with artificial intelligence in this situation, except that we were moving our characters around. But we were working with time, and time is fundamental to all physics calculations.
Okay,
so
we have to go back. That was like 10 seconds.
What does that mean that we do? Well, we need to know what this kind of rate of the update methods are. And Unity has a very nice way of doing that. So let's go back into our update. What we can do instead of some particular value here is we can use time.delta time. And that is
so I guess this is just showing that all of them can
updates,
be
and it's
on the
therefore
fixed
based on a
time
rate
rate as
from
well.
the real world clock. So now that we have our update moved, we've put this into, just save that, and let's go back and play it. This time we'll be looking at the Atom that is here. So this is the update Atom, and this is our real world timed clock Atom. Let's have a look at their rate of change when we press play. And we will now see that these guys are walking at the same rate. Now, fair enough, this guy's slightly in front, but that's because of that time offset that I tried to cater for just a moment ago. Okay, so that time.delta time is going to adjust for it. If we now go back and put that in our late update instead in here, so time.delta time, and save it, let's also, while we're in here, we'll put it inside the fixed update so we can see what's going on here. So time.delta time, and we'll save that, and press play. And we'll now see that we have them walking at a consistent rate. Okay, so the moral of this story, I guess, is that we didn't really do anything with artificial intelligence in this situation, except that we were moving our characters around, but we were working with time. And
she was just proving
what
time delta time does.
Yeah, okay.
So it means if you're going to do...
So yeah, the ultimate goal was just don't tie movement from a character to update directly like that. Like use time delta time or something so that it's independent of the frame rate. Pokemon, Nintendo should watch this.
Is that a problem?
Yeah, it's fixed at 30. If you up the frame rate, it doubles the game speed.
Wow.
Dark Souls is like that too, I think. At least the early ones. Resident Evil 2 is like that, but not exactly. It doesn't go like... it's the remake one. It's not double speed, but certain things are calculated based on your frames. So like if you do your knife swing, it does double damage if you have double your frame rates. Because it calculates it twice as fast, I guess. It calculates twice as many hits or something. It's very weird.
Mordhau had that as well, where like the speed, like if you were on a horse or something and you swung your sword, the speed that you were going like multiplied your damage if you were going faster than the other person.
That's good attention to detail. That's like a good example of that, I feel like.
Yeah. I mean, yeah, they didn't actually. Now that I think about it, that has nothing to do with the update function, though.
But it's similar, I guess, in the fact that it's like swinging the thing faster does more damage, I guess.
Yeah, that's where I'm kind of tired.
In
Okay, so I think we're good on this one.
world
Yeah.
clock meters per second type calculation.
So I think the next two are going to be the real softballs. We'll see, though. Velocity and acceleration.
So far, I think we've done like one really hard thing, which is getting to where we were, or getting to where we got in the movement tutorial.
Yeah, and I think that's what... Oh, wait, do you mean on cat-like or in this?
Yeah, cat-like.
Oh, okay. Yeah, I think we need to do... I think it's important for us to, like, just nail these basic things for sure. Make sure
Yeah.
we're all on the same page on that.
We only really know one person's way of doing it.
Yeah. Bump, 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 bump. Bump,
You're
bump,
watching
bump, bump.
Badlands Chugs.
There's a wide misconception that the speed, how fast something is travelling, is the same as its velocity, but it's not. Velocity is in fact a vector
just
value
flying.
that not only represents the speed of an object, but also its direction of travel. Velocity is a quantity that
I guess
expresses
this
the rate
could
of change.
actually...
Yeah, this is good.
Yeah, this actually might be better than I was thinking. Especially because it'll probably solidify better, like, why it's bad that I'm using velocity to determine the rotation, too. I mean, not that I need to know that that's bad. I know it's bad, but maybe it'll clue me into a
and the
alternative.
position of an object over time. Velocity is measured by distance travelled divided by the time of travel. Mathematically, it's represented as v equals delta d over delta t. The delta or triangle symbol means change in. For example, if a ball starts at 0 and after 1 second is at 10, its velocity would be 10 metres per second, and in this case in a horizontal direction. If the ball starts at 1 and after 2 seconds is at 15, then the distance it has travelled is 14 metres in 2 seconds, or 7 metres per second, also travelling in a horizontal direction. If you've already been moving objects about in a game world, you've been working with velocity. In fact, to move something, we must always adjust one or more of its x, y, or z values. In Unity, when we use translate, this is in fact what we are doing all at once, adding a vector 3 to the position of the object. To get a really good feel for how this is working, it's best to actually be coding in a practical environment. So what I'd like you to do is create a new Unity project and bring in the starter file that is attached to this video. When you open up the tanks scene, you're going to find 2 tanks set up, and they're ready for use a little bit later. But we can use some of the assets that are in here just to investigate just pure velocity by itself. So once you are in here, just go File, New Scene. And then what I'm going to do with the main camera is actually just set the background to black so that we can see what's going on a bit clearer. So solid, color, and then I'm going to make that into a black. Now we want a bullet, so I'm going to go into models where there's a shell in there. Just drag that into your scene. Now depending on where your camera is positioned, you'll either be looking at that down at the bottom or side on. What I want you to do though is make sure that in your scene view you have clipped so that you're looking directly down the Z axis. Okay, let me spin this around a bit, get out of here, and so click on that, and you want to be looking down the Z axis like this so that the X red part is going that way and the Y is going up. Once you've done that, with the shell that you just added, go over to the inspector and rotate it by 90 degrees so that it is facing across the screen, because we're going to actually push it across the screen. And then of course if you want to see it a bit clearer, then you might want to just see if you can modify the rotation on your light, or of course you could just turn it off and use ambient light. But anyway, that's all you need. You need a shell, and you can also do this with a default sphere or cube, it doesn't matter.
Spear.
So there's our shell. Now if we just double click on our shell and get nice and close to it in the scene view here, you can now actually just freely move around in the scene view. You can see its Z axis is going this way, it's got its Y axis going that way, and it's got its X axis coming out of the screen towards us. Okay, now this bullet here, if we want to push it forward, we want to push it along its Z-axis, which is what you usually do with a game character. So I'm just going back up to the assets folder where we'll just create a really quick script. So go create C# script, and let's just call this shell move. Double click on it. We don't need a start. We're just going to work inside of the update. Now inside here, we're going to put this .transform.translate, and we're going to move it along its Z-axis. So we want no movement in the X, no movement in the Y, and in the Z-axis we're going to do 1 meter per second. So that's time dot delta time. So remember, that's the time between frames. And of course, you could multiply that by the speed. So if you do want to speed up your bullet at some point, let's just create a float.
So
Speed,
just
we'll
multiplying
set
it
to 1
by,
meter per
just putting
second,
time dot delta
put that
time
down
makes
here.
it 1 meter per second by default. Is that what she just said?
I don't know.
That seems a little. I guess it makes some. I guess it makes sense.
I don't think that's right. Let me just go back.
She said like it's 1 meter per second, so
Art.
we'll put
We're just
time
going to
delta
work
time here or
inside of the
something like
update.
that.
Now inside here, we're going to
What
put
was
this
it?
dot transform dot translate, and we're going to move it along its z-axis. So we want no movement in the x, no movement in the y, and in the z-axis, we're going to do 1 meter per second. So that's time dot delta time. So remember, that's the time between frames.
I guess, yeah, that does make sense. Because 1 meter per second, delta time over time, that's 1 over 1, which is equal to delta time.
Okay. That's good to keep in
And
mind.
of course, you could multiply that by the speed. So if you do want to speed up your bullet at some point, let's just create a float speed, and we'll set it to 1 meter per second. Put that down here, and put speed multiplied in there. Okay, so save that, and switch back into Unity, and make sure that you've got your script, attach it to the shell.
I bet you it's going to go too
Move it
fast.
to there,
Which is gonna-
and then
or
press
no, never
play.
mind.
And then with each update, we're actually going to be adding 1 to it. Okay?
I
Or
feel like she
time dot
always
delta
makes it
time, I
go
should
way
say.
too
And you can see
fast
it's
and has to
moving
slow it
along
down.
its z-axis.
So
Okay,
it's
so we're
trying to be
actually
clever.
adding the vector to the position of this shell each loop. So the position of the shell is going to be its transform dot position, which is here in the inspector, and we're going to add to that a vector which is vector 3 0 0 1. And each time we loop, we keep adding 0 0 1 0 0 1 0 0 1 to it. So what you can actually do, knowing this, if you have a constant velocity, which we do at this point, is that you can predict where that bullet is going to be in, say, 10 seconds time, because all you do is you add your vector for your movement, which in this case is 0 0, let's just say 1, and you're adding it 10 times. And so it's a very simple equation where the starting position plus the velocity multiplied by how many times you apply that is going to equal the new position of the bullet. And that's one of the primary equations that is used in physics for working with velocities and positions. All right, so here's something for you to have a little think about. We've been pushing this bullet along the x direction in the world, which happens to be its z direction, so the way that it is aligned. And we're pushing it along its z direction, and it's going across the screen. What if you wanted it to go across the screen, but you also wanted it to go up at the same time, so that you ended up with a trajectory that went like that? So rather than adding this vector, you want to add that vector each time. Well, what is that vector there? Okay, it has a component of the z direction of the bullet, and it also has a component of the y direction of the bullet. So let's go back into our code and add in the same value here to our y. So it's going up at the same rate as it is going across the screen. So just save that, and let's go back into Unity and just try that out and see how we go. Okay, and there you can see it's now going up at 45 degrees because the rate of change for its z value and its y
Shouldn't
value
give us
are
time to
exactly
Dora
the
the
same.
Explorer
And then if you
try
wanted to move it
say
in
the
the
answer
x
first.
direction as well, we won't because you can't really see it on this particular screen, but you would modify this value here. Now, if you wanted to go up the screen but only at half the rate that it's going across the screen, which of these values do you think you would affect, and how would you affect it? Well, all you
divided by
do here is you
2.
have to take this and you would actually halve it, or you could even have an up speed declared,
Oh,
which
the whole
was
thing divided by
half
2.
of the actual speed.
Fuck.
Let's put an F in there for that. Okay. So now, rather than going up at 45-degree angle, you'll see that it will be a lot flatter than before, but still going up.
It's the
Okay, you can
same
see that it's
thing.
now going up that way instead.
Isn't it?
Okay, so that is working with the
Yeah, I guess
velocity
so.
and adding it here in this case to our bullet.
Yeah.
And of course, remember from our previous lectures, if you want to change
No,
the speed so it's not just
wait.
going 1
Yeah,
Well, 'cause
second,
it'd be
yeah,
like-
it is.
5 times 2 divided by 2 would be 5, and then 5 divided by 2 times 2, that'd be 2.5 times 2, would still be 5, so yeah. Alright, yeah.
and you're changing your speed up here. And you can clearly see now the difference between speed, which is just a magnitude value, and velocity. This is velocity. It's a vector, and it has a magnitude and it also has a direction.
Okay. Get me to that Excel. friend requests on Epic.
Mr. Green.
Just as velocity was the rate of change
Hello.
of position over time, acceleration is the rate of change of velocity over time, and it is represented like this.
Ridge
Acceleration
Racer.
is used quite a lot in physics systems, as objects in real life don't move with constant velocity, at least not if you have to slow them down or speed them up. Any collisions that occur will involve changes in acceleration. Anything being simulated in the real world will also constantly be under the effect of the most famous of the known accelerators, called gravity. So acceleration is quite difficult to escape. In 1687, Sir Isaac Newton published his famous 3 laws of motion. The second and more prolifically remembered is F equals ma, or force equals mass times acceleration. And it's this equation we are going to put into practice with our tanks and shells to get a real feeling for how they work.
Isaac Newton wrote Full Metal
So open up
Alchemist.
the tank scene that came with the starter file that we used in the previous lecture. And
Isaac
you should
Newton
find that
created
you've got
the
the 2 tanks
iPad.
sitting in here. And then if we zoom out in our scene view, you'll be able to find those
He
as
came
well.
up with
now,
I.
The red tank, which is called enemy, we're actually going to drive that around. And if you press play,
Why would you
can
control
see
the enemy?
That tank is indeed drivable with the arrow keys. And we'll be using its movability function a little bit later when we develop some AI for this tank so that it can actually shoot at the red tank as you're driving it. Now, the one we're most interested in this time is our tank, the green one. And if you click on it in the hierarchy and find all the different renderers that are attached, you'll see that there is a tank turret. If you double click on that, okay, it's the bit that's on the top of the tank. Then if you hit the E key and get hold of your rotational gimbal, you'll see that you can actually move that. So this will be the thing that we're going to program to go up and down in order to shoot the bullets out. Now, when the bullets come out of there, they're going to come out of this particular part here of the turret, and we want them to be facing in the right direction when they come out. So I'm actually going to add to the end of this turret a cube, and that cube will be our spawn point for each shell. So with it selected over in the main hierarchy, just right click and go down to 3D objects and cube. Of course, I always add a cube, even though you only need like a single point to do this with, but you can see a cube, so you know where it is positioned on the object. Now, it should be pretty much in the center of the object. You just got to move it in the Z direction. And then you want it facing as far as its Z axis, the same as the Z axis of where you imagine the turret is. So if you again hit the E key and then just rotate that around like that, so that you've now got it pretty much facing in the direction that that's going to
kinda
shoot.
weird.
Let me just hit the W
Like,
key to move
I
this way
guess-
to have a look. Okay, it might
Oh,
be a
this
little
being
bit steep.
empty.
I'll just bring it back just a little bit.
So you could see the
Okay, so
direction
that's a
better.
spawn point. Now, this particular spawn point, we don't really want to be able to see it. So once you've positioned your cube, you can then go
Yes.
ahead and delete the mesh renderer or
Yeah.
Oh, there it
untick
goes.
it like I'm going to do, and also the box collider. You don't want that on there at all. And if you have a look at this particular tank, there aren't any physics elements on there because we don't want it colliding with our shells. Now, let's create some shells, and we're going to do that when we press the spacebar. So we need to create a new script. So go create C# script, and I'm going to call this shoot. You want to attach the shoot script to the tank turret, not the tank itself, okay, because we're controlling this tank turret. So grab hold of it and drag and drop it onto there. Right, now let's open it up, and the first thing we want at the top is to bring in our shell prefabs. So put a public game object, and we're going to have our shell prefab. And we also want a public game object shell spawn position. Okay, just like that. Now we're going to fire these off with their own method here. So let's just create a void fire, and inside of that we will instantiate our shells. So what we're going to do here is go game object shell equals instantiate the shell prefab at the shell spawn pos dot transform dot position, and we're going to use the shell spawn pos dot transform dot rotation for the rotation of the shell, so it is facing the same way that the turret is. Right, so that's going to create a shell. So let's save that. Go back into Unity and select the tank turret from the hierarchy. Now you want to get your cube that you attached before and drag and drop that into the shell spawn pos, and then you need the shell prefab. Now that's living down in the prefabs folder. If you open that up, you can see that it's just there. You don't want the one out of the models. So select the tank turret again, drag and drop that shell over onto the shoot script. Now, in order to test this out, we actually need to be able to run that file.
And that
method.
prefab
So
is
let's
a
just-
model that also has like a script and shit on it already. Is that kind of the idea?
It doesn't have to, like, it doesn't necessarily,
Okay.
but maybe it does. I wouldn't know unless I saw.
I guess it just like she seemed like it was really important that we do the prefab one instead of just the model one. I guess I'm not super clear on the difference.
I think because prefabs are, you can instantiate them, which is what she did.
Okay.
But also, I think it's generally it would be better for something that's like going to interact with stuff to do a prefab, so you could put a script on it.
Oh, I guess, or like a rigid body or like whatever.
Yeah.
Okay.
The model is just the model.
Okay.
I guess it's a little different between animated, like a skinned mesh renderer, maybe.
Go back into the shoot script, and down in update, we're going to put an if input dot get key down is keycode dot space. So when the space bar is pressed,
Yeah,
then
do we
we're
do
going to run
keycode
that
dot
file
space? I thought we just do quotes and then
method
write space,
like that.
right?
Okay, so that's going
Yeah,
to spawn
keycode.space
our
just
shells.
returns
Okay,
the
let's go back into
string.
Unity. The other thing that I'll just point out really quickly, if we go back into prefabs
Keycode
folder, have a look
just
at the shell
returns
prefab.
whatever
It
string,
comes with its own
like,
destroy shell script attached to it, so you don't have to worry about kind of
is
cleaning that
associated
up
with
after they
it.
have been created. Okay, now it's also got on it some shell movement script, and what that has in it is the collision, so that when it does hit that red tank, it's going to do the collisions. But we'll come back and actually add a lot of more code in here in a moment. So, right, we're all ready now to press play and hit the space bar. Okay, so there we go. There's our shells being created, and they've got a collider on them, and so the physics from the rigid body and the collider is going to be working on there, as you can see. But what they're not doing is actually going off in a forward direction. So let's stop playing, go back to your shell prefab, and what I want to do is we're just going to turn off the rigid body and the capsule collider just for now. So untick them or remove them. In the case of the rigid body, you will actually have to remove it. And now when we press play, we will get shells created, and they're all in exactly the same spot, but they will destroy themselves after a while. Okay, now that we have them, we can actually manually program them to fly forward. Now that's going to happen in our shell script. Okay, so let's go back and grab that, which is in scripts. Go to shell, and let's put down in the late update. So if we want our shell to move straight across the screen like we did before, can you remember what code we had? Well, we had this dot transform dot translate, and we set it to be 0, 0, and then time dot delta time to go 1 meter per second in the direction that it gets spawned along its z-axis. Okay, let's save it, go back, and we'll just check that's working. So when we press play, the thing will be spawned, and then it's going to move off. Now, it's moving at a constant velocity because we're always adding 1 meter per second type of thing with every loop, at least the time dot delta time, so it will be consistent. If there was acceleration involved in this, you would see the bullet speeding up or slowing down, but you don't. It just keeps going until it sort of runs out of life, which I think is about 3 seconds. Okay, so let's now add in some acceleration. So acceleration is going to be based on the formula F equals ma. Now, if we rearrange that equation, we end up with acceleration equals force divided by mass. So we can actually use that fact in order to give the shell a mass and also give the shell an initial force. So let's add those in. Let's add in a float mass equals 10. Now that's 10 kilograms, and float force equals 1,000. Then we also need another float for our acceleration, and then ultimately we'll need a float for velocity. Actually, velocity isn't really velocity, is it? It's speed. So I better use the right terminology. And we're going to be, first of all, calculating the speed in the z direction. It doesn't really, I guess, become velocity until it becomes the vector that's sitting down inside of here. Okay, so we have that. Now let's do our calculation, which is going to happen down in our late update. So in here, we will put acceleration equals force divided by mass. And then acceleration is the amount that you add onto the velocity each game loop. So we're going to have our speed in this case, so we're just using the z part of our velocity. So speed z, and that will be plus equals acceleration times time dot delta time, and then that means we can just replace the calculation down here with speed z, and therefore our velocity vector is 0, 0 speed z. Okay, let's try this out. So save it, let's go back into Unity, and we'll press play and hit the spacebar. Now, very fast because our shell is accelerating away from us very, very quickly. Let's go back and slow this right down. So let's give it a force of 10. Okay, and we'll save that, and we'll come back in here and press play, and you can see how it starts off quite slow and then it just takes off as the acceleration picks up. So that's the compounding effect of constantly adding acceleration over and over again to the bullet, in this case the shell. Okay, so time for a little bit of a challenge. We've currently got our shell accelerating in the positive direction as far as getting faster as it goes along and the longer that it lives. What I'd like you to do is think, what would you include into this code?
Subtract gravity.
So that it decelerates after it has been instantiated. So pause the video now.
Never
Have
mind.
a little bit of an
So it accelerates and then decelerates, or it just decelerates, I guess. if it's just deceleration, you just flip it, right? It'll just be... Well, actually, hold on.
There's a guy in the way.
Yeah, roll it back. Get out of the way, guy.
Acceleration equals force
Would you
divided by
divide
mass.
acceleration by time, delta time?
Maybe. I don't know.
So I want to say subtract, but it should be going to 0 and then stop, right? It shouldn't go negative, should it? Because then it start moving in the opposite direction.
Yeah.
So my first thought was just speed z minus, just replace the plus with a minus, but then that would make it go in the opposite direction. So it should start...
No, it wouldn't. Would it? Yeah, it would.
Because it's speed z minus, or speed z equals speed z minus acceleration times time dot delta time. And in this case, acceleration is 100, right?
Is it?
Because it's... Oh, never mind, not 100, it's 1. It's force divided by mass, right? It's just 10 divided by 10.
Mm-hmm.
So it's not doing anything, actually. Acceleration is... I guess whatever, because it's plus. Speed equals that plus itself.
Yeah, so it's just increasing its speed.
So even if it was division there, it would still be accelerating, though. Because it would keep adding on some... It would just be accelerating way slower. So maybe there is some sort of... Maybe subtraction is the right train of thought. And we could just put like a cap where it just says like if it's below 0, stop subtracting kind of deal.
Yeah, you still have to do something though to set the... Oh, maybe it's divide. Speed divided by acceleration. Because then it would never go under 0.
But would it just never stop moving then? Like, because it would never like actually hit 0?
Yeah, but I feel like we have to have some...
And we would despawn it after like 3 seconds, so it doesn't really matter.
Yeah, but this is a 2-part answer. It's not just like, oh, flip this. It's flip this and add. It needs to have higher acceleration at the start. I guess it has... you set acceleration at the beginning.
Well, it doesn't have to be higher acceleration necessarily, right? It just has to be... It starts at some acceleration and then decelerates from there.
Yeah.
And acceleration and deceleration are the same thing, just in different directions. So it should, like... I guess I'm going to say my answer is change the plus to a minus and then add a check for if it hits 0 to, like, set, like, a minimum.
Yeah.
But I think division... I feel like something's telling me division should be there. You're right about that, but I don't know where.
I don't either.
Okay, let's see what she says.
Decelerates after it has been instantiated. So pause the video now, have a little bit of an experiment with that. You might be able to achieve it a few different ways, and then I'll come back and show you how to do it. Okay, how did you go? Well, if you remember, acceleration equals force divided by mass. Now, it's a solid shell, so we can assume the mass of it is not going to change over time. The force, however, is something we can control. Now, each loop, we could actually make force get smaller. So down here, let's put force minus equals...
There you go.
Let's go with something little so we can see the effect slowing down. That still might be a bit fast, but we'll see. So
that makes
we're going
sense.
to decrease force each loop so that the
So
acceleration...
it is a one-step.
Each loop. So let's go back.
And it is a division thing.
Press play. Okay, so we'll hit space.
What?
No, that's speeding up.
Okay, still possibly not enough. So go back into shell and we'll actually remove 1 from it.
Well, she
Save
still
that
has the
and
acceleration
try it
happening.
again. Okay, press play. Interesting effect there. Okay, so you can see that it's accelerating in there. Then the force eventually becomes negative force, so it actually goes back again. It's quite an interesting sort of bouncy bullet thing. Let's just while we're in, have a little bit of a play. Let's try 0.5 from our force, and we'll go.
Oh yeah.
And
Well, it's...
then
Yeah, what the
No,
fuck?
yeah.
Yeah, that's not the effect we're after, but it's quite interesting. So what you could do is actually put a math.clamp
That
around
ever
here so
happen
that
when
when
you're
it did get
taking
to
a
0,
shit, dude?
it
Clamp.
would stay there.
I was gonna say clamp, but I
in
felt
this
like
case,
she
we've got a
wasn't
tank.
gonna
And the tank
try to
essentially has
confuse
an
us.
explosion in it that
Yeah.
pushes the shell out of the turret. Once the shell has left the turret, the shell gets no more force added to it, at least not from the turret itself. So after it has been instantiated and after it has had its first bit of velocity calculated for it, its force really should be set to 0, and it should just stay at 0 because there's no more forces on it. So let's now save that, and we'll come back here into Unity and press play. And now we're just going to get that, which is pretty similar to what we had in the first case when we just had our velocity. And the reason is that once you set your force to 0, there's no more acceleration, so it's just going to go and have a constant velocity again. But that is, in fact, the case that you get with bullets because they only ever have that force added once. So we can
Now
also go back
she
and
adds
just ramp
gravity.
up our force amount so it goes a bit faster.
What?
Now,
Did
there's
she even
another
add the
acceleration
clamp? What
in-
did she just set it to 0. What did she even just do?
She said could.
Oh, okay.
Involved in our flying shell. Do you know what it
Damn
is?
it, I missed that.
Well, it's actually gravity.
Damn it,
With bullets,
Hey!
because they only ever have that force added once.
Successful
so we can also go back
call.
and
Spoilers.
ramp up our force amount so it goes a bit faster. Now, there's another acceleration involved in our flying shell. Do you know what it is? Well, it's actually gravity. So gravity
Wow.
has an accelerative effect because it is a force due to the size of the Earth on the shell, which makes things fall towards the Earth. So, can you think about how you would modify your code to make your bullet go downwards as well as go in the Z direction? Okay.
Aw. So just create a different speed variable that's just speed y instead of speed z, and calculate it in a similar way, I guess, where it's like speed y equals speed y plus gravity times time delta time or something like that.
Yeah,
And then gravity is 9.81. And you just set
Yeah,
it as a
that's-
constant.
probably it.
Well, it would be, I guess, yeah, you could do that, and that would just say it's negative speed y.
Yeah.
I don't know. I think she might do it different than that because that is a little bit of a roundabout way to do that. She might just do it a smarter way where it like goes downwards in negative direction, but we'll see. Wait, shit, that's probably. Do you think
Yeah,
if we
she-
just put negative in front of speed z, it would have decelerated? Or no, it would have just went in reverse.
No, yeah, backwards.
Okay, so pause the video now while you have a think about that. When we come back, I'll show you how it's done. So, how did you go with that? It's an interesting thing, the acceleration from the Earth's gravitational force. So the force in this case is going to be our downward force. So let's go over here to our properties. Now we want to float for our speed y, because that's our y coming down, or moving our bullet in the downwards direction. We also need a float for gravity. And gravity, does anyone remember from high school physics what it is? It's negative 9.8 meters
Oh,
per
she just
second
makes
per
it
second.
negative there.
And then we also need another
That makes sense
acceleration. So let's
because
create a
it's in the vector
float
at the
and we'll
end,
G excel.
so it decides the
So we now have
direction.
these values. Let's just put an F on there. And we're going to go down into the late update and calculate the gravitation acceleration. So G excel, which will equal our gravity divided by our mass. And then we have our speed y, which will be plus equals to G excel multiplied by time dot delta time. Okay,
Yep.
and then what we can do is put our speed y into there.
Okay, hold on.
Actually, I think that this is going to make. This is going. Because she's going off of her z vector, so she's also going off of her y vector, so she's going to be going up at an angle, I bet.
You think so?
Yeah.
Because I guess what confused me is that it's adding. Like it's speed plus.
Adding a negative number.
Yeah, but like, wouldn't it eventually become positive then? I guess.
How?
Like, I feel like it's gonna. Because it's speed plus, like, negative whatever this negative force is, right? So speed equals speed.
Negative 9.81 times a second, so negative 9.81. So speed
Well, it's
is
divided by mass too, though, right?
oh yeah.
So it's
I guess that's true.
0.981, I guess.
It's still 9.81 to times 10 to the 10 to the x. It's still it's still just one number. Speed plus negative and then plus negative and then plus negative and then plus negative. It's just going to keep being negative.
Oh, okay, yeah.
Okay, so it's going to be our y vector influencer, and the other one will still be influencing our z. So let's save that, go back to Unity.
Let's see if I'm right.
Press play, and let's try out these shells. Okay, still very fast. You can't actually see them looping around. Let's just change the force down. We just want to be able to see them make that arc as they go across the screen. So let's just change this to, say, 200 and save that. Let's play that again, and we can now see the arc. Okay, so you see the arc, it's coming out up there. Now, if you were to grab your tank turret and just rotate it manually up like this while you're still in play mode, and you can see that you'll get a different arc when you go up there. Okay, obviously this isn't perfect.
This right?
What we're going to do is come back in the next video and we're going to fix all of this up. We're going to use the Unity's physics system to simulate the shell itself moving, and then we're going to build in an AI capable of figuring out where the red tank is and how to calculate what these arcs are going to be so it can actually hit the tank with the
That doesn't make sense to me.
So wait, what's the problem?
I feel like she's tilting gravity. Because when she does Z, it shoots forward because she tilted the object. She like starts off the empty by like tilting it forward, and then when she does
that's true.
When she translates along the Z.
So gravity's gonna be like at an angle to the ground.
Yeah, it's not
like a world
space.
Z, it's a local Z, yeah. Or Y.
That's weird.
I mean, she said she's gonna touch this system up in the next one.
Yeah.
So maybe that's something she addresses, but that is a good catch. That I think you're right.
Maybe she'll bring it up later.
I mean, does it look like it's affecting the arc of it really though?
It looks like it could be doing either.
Rotate it manually.
It looks like you could pass it as either.
And you can see that you'll get a different arc.
I guess I could see if like
it's not going straight down.
Yeah, its gravity is like this.
Yeah. It's like pulling in a circle.
So it has one force going this way and then one force going this way. So its actual arc is like some mix of it.
Arc when you go up there. Okay, obviously this isn't perfect. Okay. What we're going to do is come back in the next video and we're going to...
So we'll see if she addresses that. So we're on to the last chunk here.
Nice.
Trajectory. Oh, it's a two-parter.
Particles that are emitted at a certain velocity and angle that have no further force applied to them other than gravity form the curve of a parabola. We call this type of motion projectile motion, and it's the exact thing our tank shells are simulating. There's a lot of mathematics and trigonometry involved in working with parabolas, and an excellent breakdown of it is all on Wikipedia, where you can find more information if you want to delve in deeper. But let's just go over a few of the basics. All motion of the projectile we consider in two directions, horizontally, which is its x coordinates, and vertically, which are its y coordinates. After the projectile is fired, it experiences no further acceleration in the x direction. Acceleration remains constant. Though wait, I hear you say, or I hope you said, that would mean that an object would never stop moving. And indeed, in a vacuum, that is the case. Of course, in the real world, there's drag and wind resistance and all other matter of things that you could consider. But for simplicity, we aren't going there. Now, the y direction of acceleration is always going to be our good old friend, gravity. You can see in the animation how gravity remains constant vertically no matter what the angle of projection is. So acceleration matters in projectile motion are fairly straightforward. And so too are the ones to do with velocity, if you can remember your high school trigonometry. There's a great Wikipedia page where you can brush up on those skills.
Took trig in 8th grade.
So the velocity of vector that the projection begins at is denoted v0, or the starting velocity. And the angle this vector makes with the horizontal is alpha. Using this knowledge, we can construct a right-angle triangle to break velocity into
I couldn't have taken trig in 8th grade.
Horizontal direction. Using trigonomic ratios, we can further work out that Vx
I took trig in
V0 multiplied by cosine of alpha And Vy equals V0 multiplied by the sine
Junior
of alpha
year.
minus
So she's
GT,
just doing,
where
what
GT
is it called?
is the gravitational effect at
Kinematic
any point in
equations
time.
at this point.
Remember that the acceleration
Yeah.
due to gravity
Just
has a
if you
compounding
have
effect. So
if you have
each
two
game
of them,
loop or
you
time
can,
interval that we are adding another
or
lot of
three of
gravity
them,
to
you can
is
just
going to multiply. So if we
approximate
do
the
this
rest.
t number of
Or
loops,
not even
then we have to
approximate,
multiply
get the
gravity by
rest.
t to get the correct amount. Now, from this diagram, if we know Vx and Vy, we can calculate the initial speed of the projectile, which is the magnitude or length of our V0 vector. And to do this, we use Pythagoras' theorem thus. For what we want to use the principles of projectile motion for is to work out
Whoa.
the angle the tank needs to aim its turret at in order to shoot a shell with a known speed and hit its target where the target's position is known.
Why is it
So to
doing it
calculate
like
this
that?
angle, the formula that can be used is tan of the angle equals the speed squared plus or minus the square
Oh,
root
she's
of
just
the
shooting
speed to
those.
the
She has
power
like a
4
bunch of them
minus g multiplied by
on,
gx
probably.
squared plus 2y multiplied
There's
by
like
the speed
5
squared all
at
divided
the
by
source.
gx. If you haven't
Maybe
used
it's
an
not.
equation with the plus minus symbol in it before, what it means is that there can be two possible solutions. In this case, there could be two angles that could be used to hit the same final location. But that's the nature of parametric equations. And you can see this in the animation shown. For all the final hit points of the projectile, there can be two starting angles. So enough with all this mathematics. We have the equation that we need. Let's get back into Unity and implement it. At the top, we first of all need to get hold of the target so that the tank knows where the position of our target is. So public game object target. Now we also need to set up the speed that we're going to use for our projectile. So here I'm going to put float speed and we'll make that 15. Initially, of course, you can change that as you need to. And we need one other thing because we're going to turn the body of the tank as well. Remember, this script is sitting on the turret. So let's just grab the body, public game object parent, and I'll put it in this extra pointer to the parent rather than keep doing a get component or a find parent, all those sorts of things, so that we have it more efficiently stored inside of the code. Okay, so let's just save that and we'll set a few things up back in Unity. So we want to select on our tank turret, and when that code loads, we need the target. So the target is our enemy, and we can just grab the parent object for our target there, and then for the parent object, we just want the top of the green tank, so tank from the hierarchy. If you remember in the previous video, what we did with our shell was turn off all of the wonderful things that make it a physics object. We now need to turn those back on. So you want to select your shell from the prefabs folder, come over to the inspector, and we want to turn our capsule collider back on, or add one if you deleted it, and we're also going to add a rigid body. Now we're not going to do anything with these, we're just going to leave them as the default values. However, do make sure that the capsule you have ended up putting on the shell prefab actually does fit it quite neatly. Unity usually does a pretty good job. Let's just check that out while we're here. Just zoom in on our shell and lift it up, and then see if we can see our capsule. Okay, so I can see the capsule. There it is. You can see it's not actually the best capsule, so I want to change its height. Oh, actually I want to rotate it around its z-axis, so it faces that way. Then we're going to change the height and just make it a little bit smaller, and then we want to change the radius as well to something a little bit like that. Okay, so now that you've got that on there, just again select your shell, which is now in your hierarchy, and make that an override for your prefab, which means, if I bring this in a bit, you want to click on overrides and then apply all to your shell. Okay, so we can just delete the shell out of our scene. Let's come back to our 3D view and select the shell again, and let's go over to the script that we put on there. So we've got this shell script, let's just double click on there, which does the explosion, and we did all this acceleration and all that sort of stuff in there. We're not using that anymore because we just want to use the physics system that's in Unity. So we'll just get rid of all our experimental code that we had, which are all of these variables at the top and then anything that we've got sitting inside of late update. Now I'll just comment that out so that if you get this file as the solution file, you'll see that I've taken it out and what I did take out. Okay, so let's save that, and now we're ready to go back into the shoot script. What we're about to calculate is a trajectory, but in a single plane. So when we shoot, we're only really working with X and Y coordinate systems. That means for our little tank, we want to turn the tank to face towards the target before we then bother about lifting the turret up and down. So let's put that code in first. Okay, so underneath our spacebar for firing, which we will modify a little later, let's put in some code to slurp the tank around to look at the red tank. So we need a vector3 called direction, and that's going to equal the target dot transform dot position minus the parent dot transform dot position, and we're going to normalize that so we get a unit 1 sized vector. Okay, and then we're going to create a quaternion look rotation, and this will smoothly allow us to turn from one facing direction to another. So that's going to equal quaternion dot look rotation, new vector 3, direction dot x 0, direction dot z. Okay, so then we can set the parent, which remember is our tank's body, dot transform dot rotation to equal a quaternion dot slurp for the parent dot transform dot rotation to the look rotation, and then we're going to turn around at the speed of time dot delta time multiplied by turn
So
speed.
the gun and the
which we
body will
haven't
kind of move
yet
at like
declared.
a different rate.
Okay,
Is
so
that the idea?
let's just check everything else is okay. Go back up to the top. We're going to add in a property for our turn speed. Again, you can adjust this if you like. So
I don't-
put in float, turn speed.
I don't know. I
and
think
we will make that 2 meters per second. Okay,
I
so
think
we've got that. Let's
she
just save it.
commented
What we
out
should be
all
able to
the
do at this-
stuff that this is replacing.
I just mean right here because it's
Oh,
right here you just change your look rotation, and then here you're changing the parent transform rotation. So it seems like she's changing the gun rotation and the bodies of the tank's rotations like independently. Like you would expect to just move the whole thing, I feel like, but I guess we'll see.
wait, what is? I don't get it.
The quaternion look rotation is basically it's essentially a lerp of just like you give it 2 quaternions, like 2 rotations, and then it'll blend between them, I think is the idea.
Hmm.
So you're creating a quaternion called look rotation. Actually, wait. Yeah, you use that here in the actual slurp as the thing it's rotating towards.
Mm-hmm.
Oh, okay. Maybe I did misunderstand this. Hold on. So you create a direction, which is the difference between the 2 things. Then you create a quaternion called look rotation that gets that creates a quaternion in the direction of that distance, I guess. So it's just the line between the 2 things is the quaternion now, I guess is what that's doing, called look rotation. Then you change the parent transform rotation via slurp between its current rotation and this new quaternion that you've created. Okay, so you are just turning the whole body. You're not turning them independently.
Okay.
I thought this top bit was just changing the gun's rotation, but it's just creating a quaternion. I think it should, the whole base should move, I think, if I understand this right.
Point is drive our little red tank around and have the green tank follow it. Okay, so once that kicks in, I'm going to be able to drive around, and now the
Okay.
tank is following me. Okay, great, so that works. Okay, so let's go back into our shoot script, and at this point we can start to tackle that mathematical equation. Right, so what I'm going to do just under the update is I'm going to create a new method. That's going to be a float, question mark, calculate, angle. And we're going to send it through a bool for low, and I'll explain that in a moment. So what the float question mark will allow you to do if you haven't seen that before is that you can actually return a float or a null value, which is really nice. So if we take a look at the equation is actually going to return us something very strange if the part underneath the square root happens to be negative, because the square root of a negative number is an imaginary number. And trust me, we don't want to go there. We're not working with imaginary numbers. And in fact, if you do end up with an imaginary number after you've done this calculation, then the tank is actually not in range to perform the correct trajectory, which is good. So we can actually test for that. Okay, so we're going to do this step by step and break the whole equation down. First of all, we need the direction to the target. So vector 3, target dir, which will equal our target dot transform dot position minus this dot transform dot position, and then of course a little bit of cleaning up of my bad typing, transform dot position. Okay, so there's our vector. Then we're going to get our y component. So float y will equal our target dir dot y, and then we want to...
Oh, so they are rotating independently. So that's what this bit is doing. So the body's going to rotate along the Z or the Y, and then the head is going to rotate around the Z, I think.
Oh, okay.
Because it'll look up and down to like calculate the trajectory, and then the
Yeah.
body spins the whole thing. I think
Yeah, that's
what
how
it
my
is.
first person thing works.
Okay.
Because that way the forward doesn't change when you look up or down. Like the forward of the main body,
Yeah.
it's always pointing up like on the floor.
Target dir dot y, actually set that to 0f. And what that's going to do is flatten out that vector and give us the leftover x value. So float x is going to equal target dir, but we want to get the magnitude. So we want to get the length of it, because that's the distance between one tank and the other. So magnitude. Okay, then we have gravity. So we're going to define gravity, and that equals 9.8 f. And in this case, actually going to be a little bit more accurate, 81 f. We don't need to say negative because the calculation actually assumes that gravity is negative anyway. That's why there's minus sign in there. Okay, so next we're going to calculate the speed square root, which is going to equal speed times speed. Then we want to float under the square root equals the equation that's going on under there. So that's s squared. So that's s square root multiplied by s square root, which gives us s to the power of 4, minus gravity times, in brackets, gravity times x plus 2 times y times the speed squared.
Is there no built-in power function?
There is, but it's slower to like put it in the it's slower to put it in the line, I guess. It's like better to save it as a variable if you're going to reuse it over and over.
Okay.
But yeah, there is.
It just generally seems like it's a better practice to just write it out as x times x times x or whatever.
I think it's so that because I know squaring is one of the harder ones. Or square rooting is like one of the harder ones. But like yeah, if you write square like a couple times in one, like float equals and then like square root of square root of square root of square root, like that would be harder than doing, or that would be like more intensive than if it had just like a value called square root and it doesn't have to do that operation over and over.
Okay.
Right, great. Now, we've got our under the square root calculation. If that under the square root happens to be greater than or equal to 0f, then it's okay. If it's a negative, we're going to get an imaginary number when we try and find the square root, which is definitely no good to us. So if we're inside this if statement, at this point we know that we have some angles to work with. So float root equals mathf dot square root, and we will then find the actual square root of that under the square root section. Okay, so then we can have two angles. So float, our high angle is going to equal s square root plus root, and float low angle will equal s square, so that's the speed squared plus root. Okay, so now we need to make sure that we've divided those values with the part that's on the bottom, which is gx, and we also need to get the inverse tan of those. Now there's two possible angles here, which is why I'm sending through a bool here for low. So I'm going to say if low, then what we're going to return is the mathf.arctan or inverse tan 2 of the low angle, and this will be gravity multiplied by x, and then we want that multiplied by mathf.rad to d, because that will be in radians, but we actually want it to be in degrees. Otherwise, if we're not wanting the low angle, we want the high angle, so we kind of want our turret to point much higher. Same thing, except in this case we're just going to change this to high angle that we're passing through into there. Okay, now if this bit fails, then we've got an else. So else we will return null. Okay, so there's our calculate angle and the deciphering of that mathematical equation. And when we come back in the next video, we will finish this.
Okay, so what is low? Where is this coming from?
If you go back a little bit, she draws it. It's the two possible angles to get to the same spot.
But like, how is it deciding which one to use?
It has that input bool.
Oh, so when you use it,
Yeah,
you would
you
say,
say,
is it low or not?
yeah.
Okay, okay. I think I'm following that overall.
Cool.
Degrees. Let's go straight into the code again. So I'm still in the shoot code. Just above our calculate angle, I will create another method called float, which will also be able to return a null, and it's called rotate turret. Okay, so in this particular method, we're going to call calculate angle, so it'll be our float question mark angle equals calculate angle, and in this case, I'm going to go for the lower range of angle, so I'll put true in there. Okay, so then we're going to say if angle does not equal null, so we did actually get an angle, then we can go ahead and rotate the turret. So to do that, it will be a this.transform .local Euler angles equals a new vector 3, and in this case we're using the Euler angles rather than quaternions because the Euler angles allow you to set the rotations around your x, y and z axes, and because we've got a turret and we're really only rotating it around its x axis, then that's all that we need to do. So we don't need to complicate things with quaternions in this case. Okay, so it will be a new vector 3. Now initially our turret is flat, okay, so it's horizontal. That's actually going to be 360, and as we lift it up, it's going to go sort of into the negatives as such, but it's not. It's going to count backwards from 360 degrees. Okay, so we're going to minus, and we have to make sure that we throw our angle to a float, otherwise it won't like us very much. And we want a 0f there and a 0f there for our other rotations of axes. And then finally, we're going to return the angle. Okay, so now we have rotate turret. So what
is this? The float in parentheses thing? I don't recognize that notation, I guess.
Probably because float is a question mark, or angle is a float question mark, so you probably have to specify when you're using that double type.
Oh, so this is just calling that method? It's just that because it's a weird type?
Well, yeah, it's already set to, angle is set to calculate angle, which is of float question mark type.
Okay.
So it's
you're
yeah,
saying that it is a float, it's not a null, I guess?
Yeah. Or the float value of it, I guess.
Okay.
Yeah.
Call rotate turret. Let's do that up inside of our update. So what I'm going to do here, and it doesn't really matter, I guess, whether you put it at the beginning or the end, is that I'm going to create another float, and for angle equals rotate turret. There. Okay, so that's now going to face the target. Great, so save that. Let's go back to Unity and we will press play. Right, so once that kicks in, we should have the ability to drive our tank around as we did before, and then we'll see that the turret actually changes its height. So we still have the code that will fire in there. And look what happens when we press fire. Not a lot.
That's pretty cool.
Because we've taken away our calculations for the speed of our bullets. But what we want to do instead is actually put them inside of our script.
I wonder if I could apply that to just like a bone on an armature and have it like that's how you would have them like have their head track you and shit like that. Like as an NPC.
I bet it is.
Here, and we want to do it when we fire out the shell. So we're going to do that by grabbing hold of the shell's rigid body and setting the velocity of it to the speed value here, or at least the magnitude of the velocity. So it's going to be shell dot get component, and we want the rigid body dot velocity. We're going to set that equal to the speed multiplied by a vector, because we don't want just speed. Speed is a value which is a magnitude of a vector. The vector in this case is this dot transform dot forward, because that's the z-axis that we want to shoot along. Okay, let's save it, and we'll have another go. And this time, we'll find as we're moving our tank around and we shoot, that we do, in fact, hit the tank. And the code's already in there that's going to give you the little explosion. Okay, how to get...
So the reason that works is because we have that speed as a fixed value, and we use that value speed in the, like, trajectory calculations already.
Yeah.
Okay.
I guess that is what it is.
So that tripped me up for a second of, like, shouldn't that speed be like a calculated thing? But I guess because the arc is what's changing, not the speed. So the speed
Yeah.
is fixed, and then it calculates the arc based on that speed.
Yeah, I guess that's pretty important.
Okay.
Get this to do it automatically. Well, that's quite easy. Rather than having a get key down input, we can just replace that with a little bit of logic. So first of all, let's get rid of our input, and I'm going to put fire down, take it out of there, and put it underneath where we've calculated the angle, because before we fire, we're actually going to say if angle does not equal null, and vector 3 dot angle, the angle between the direction to the enemy and the tank's actual forward vector dot forward. So while we're turning, that angle's going to be quite large. We're going to say when it becomes less than 10 degrees, then we want you to start firing. And if you want it to be super accurate, you could bring this angle down.
Oh,
or if you
so
want it to
maybe
be really
that's
bad
why
at,
in that
firing
example it was
and
just like a
its accuracy, just
barrage.
increase that number. So let's just say
There were like hell of
back
them were
into
missing.
here. And now when we press play, we're going to end up with a barrage of shells
Okay, that's
fired at our red tank. Now, if we move off, because that if statement's not satisfied until we get to the right angle, it will stop shooting until it can, and then when we go out of range,
that's pretty
it's just
fucking
going to
cool.
stop because it can't actually hit us. But then when we come back, it's going to readjust. Now, two other things that we really should fix are the firing rate, because it's a little bit ridiculous, and also if you have a look at the shells, they're not facing
they're
the direction
colliding with
in
each
which
other?
they're going, and that's probably difficult to see when there's so many
That
of them. So
too,
first of all, let's
yeah.
fix the problem with being able to shoot. So let's go back into our shoot script, and we're going to add top here a little boolean. So we'll call it bool can
That would be a
shoot.
layers thing, right?
Set that to true.
Yeah.
And then
Doesn't
inside
have
of
to
the
be,
fire,
but-
we will say if
Yeah,
can shoot.
I did that for
then we're
the.
going to shoot.
Well, actually, I don't know. Maybe it's just collision
And then
detection.
once we've shot
Yeah,
one shell,
no,
we'll
yeah,
go
that
can
is layers.
shoot
That's what layers are.
equals false. Now that was going to stop a whole succession of shells happening. But when do we set can shoot back to true? Well, we need to invoke a method to do that. So we will invoke, and we'll call it can shoot again. And we want to invoke it in, let's say, half a second between each shot. Now that means we need to put another void method up here called
Damn.
can shoot
I didn't know you could
again.
do that.
And inside of there,
I've been
What?
using this fucking dumbass method of where I guess it's probably not that dumb, but every time I've been in a situation like that where I wanted like a cooldown, I create like a stopwatch item and then like a countdown, and then I compare them against each other. That's cool that you can do that.
we will put can shoot equals.
Damn, I really need to remember that.
true.
That's
And that will set it back again.
Yeah,
Okay,
that's.
save that.
I,
Let's go
it
back
all. I remember
and play, and this time we'll be
that
able
always
to see our
seemed
bullets
like-
a little bit clearer.
hacky.
Yeah. So see that
Just
the
like
shells
roundabout
are
at
coming out
least.
and they're facing
I
the
just couldn't
direction.
think of
They don't
anything
turn
else.
And face
Yeah,
in
and I
the
wouldn't. I
actual
couldn't
direction
either.
of travel. They just come out.
It just
and they're
felt
fixed
like
facing outwards,
off.
but we want them to
Mhm.
turn through a nice.
Or it
arc,
felt like
a
it
nice
didn't seem like
parabola.
something they would have
The
taught
easiest
us.
way to do this is set the rotation of the actual shell to the velocity of the shell at any
Uh-oh.
time, because remember, velocity has a direction. So why not?
I
use
guess
it?
actually it's
Okay,
fine
so
for a
let's just stop playing.
projectile.
We'll
It
go
doesn't really matter.
back
Yeah.
into our prefab for our shell, and the script we will add. That
No,
into our
lady,
shell
don't
script.
do
And you can do
it.
it this way, or you go back into the script and do it in there. So at the top, let's put a link to our rigid body so that we can get hold of that. So rigid body RB, and then down in the start we'll grab that. So RB
Make
equals
it
this dot
public. Make it
get
public.
component
Oh, never
rigid
mind.
body.
Oh.
Like that, and then in our late update we're going to put this dot transform dot forward, which is our forward vector of our shell, and that's going to equal RB dot velocity. Okay, so we've now turned our shell. So let's just save that and have a look at the effect of it.
I wonder if there's something to that. I don't
Maybe,
get
yeah.
I don't get velocity like from a calculated thing like that. We have velocity as a value that we're creating in the
Yeah.
moving sphere script.
And setting every frame,
So
right?
I wonder if that is something. If I just get like if I just derive the, or I guess I don't know, just steal the velocity from the rigid body
Mhm.
instead.
That's where we set it.
I guess that's true. Yeah, we set it to the rigid body, and I just take it back off. It would probably be the same thing.
But it might be more correct or like accurate to what we're seeing.
I'm gonna give myself like 15 seconds to do that. Hold on. Moving sphere. Or no, wait, it's an update rotation. Update rotation. Moving, jumping. set that to rb.velocity. And then I have to create what RB is. So, oh, whoops. Rigid body RB. No. Rigid body RB. And then I'm just going to make it public and just drag the one from my script on there. Or the one from my character. So update rotation, RB. That's where my rigid body is, right? Yeah. Okay, are you okay with that? No errors with that? And I'm still going to project it on a plane just to be safe. Let's see if that does anything. Nah, same thing. Let me try running into stuff. Actually, it feels like it actually did help a little bit, but then there's still that. It's happening a little less often. No, maybe not. Oh no, wait, I think the biggest indicator is when I'm in the water. Because if I swim into like a bunch of little objects like cans, she just spins all over the fucking place. Yeah. Okay, so I don't think it really changed much.
Yeah, more work. More work to be done.
Worth trying though.
Yeah.
Press play. And now when we shoot, you can see the shell actually travels along its trajectory, which just looks an awful lot nicer. Okay, and of course if you want to change the speed at which you're shooting, then you can reduce this can shoot time. So let's just halve it so we can see a better stream. Press play. Okay, there we go.
I wonder if she's going to do like a
stop.
bloom, so it's not like 100% accurate every time.
Now this is the low angle that we've chosen to use in this case. What if we get the high angle? So let's go back and grab the high angle.
That was something I was
we pass that through inside
gonna try to figure out once I did that shotgun idea.
So if we now set this to false,
but this is kind of
and save it.
This is
come back,
basically
it's
the
going to give
shotgun
us a
idea.
higher angle, and you'll immediately see that because the turret. So now you get that sort of effect. You're still hitting.
This is the better
tank,
way to do it.
but
We should
you've got
always
a
use the
higher
high angle.
trajectory, and I guess that's probably good if you're trying to shoot over a wall or something. Or you have got some particular.
Oh, it's not
artillery
even
that
hitting
actually
him. It's
has a turret
despawning
that's
before it
already
hits
facing
him,
the
I
other
think.
direction. And you can see there with that particular.
it takes more
high angle,
time.
It's much harder to hit from a distance.
It just looks cooler, I feel like.
Okay,
Yeah.
And it's
so that's
easier
the
to
end
dodge.
Of our little tutorial
Definitely.
for putting together this AI shooting tank, which is calculated.
Okay. I think this is a good format. I think this is a good way to do this. Is we do one stream where we just watch it and talk about it, and then we'll come
Yeah.
back and then we'll implement it. I think that is a good point. 'Cause
Monday
that'll
is a
give us
good,
time to sit on it.
and that way we're not doing like if we were following along, we'd probably still be in like the first one.
Yeah, because it is a lot of work adapting that because you have to change, like the way she's doing it isn't the same way we want it. So we're
Yeah.
gonna constantly be doing little small changes.
So just getting to know her whole system first.
Yeah.
That way also we're not just like, oh yeah, she might change this in the next one. I don't know.
All right, cool. Well, physics of AI is wrapped up. We got that done in an hour and 20. That wasn't too bad. That was definitely more informative than I expected, But
Hello, friend.
it got the job done,
I'm here live on Facebook. Just eating some beans. I got some red beans here. Just eating some beans. I got some red beans here. Hi, Dean Miller. I'm just over here eating beans. I've seen it. Two people talking on the same screen. Just eating some beans. I got some red beans here. Just eating some beans. I got some red beans here. Hi, Dean Miller. I'm just over here eating beans. I've seen it. Two people talking on the same screen. I'm trying to see if people can call in on Facebook Live and do a split screen with me. I'm just over here eating beans. I got some red beans here. Just eating some beans. I got some red beans here. Hi, Dean Miller. I'm just over here eating beans and dreaming big, thinking of big thoughts, having big dreams and stuff. And dreaming big, thinking of big thoughts, having big dreams and stuff. I just got a text message. Hey dude, what's up? I'm just over here eating beans, eating beans straight out of the can. Yeah, I just cracked open this can of beans and ate them away. No spices, no preparation, just ate them straight out of the can, and they're pretty good. My bro from San Diego joined the call. I have another viewer now. Somebody else joined in. So I'll eat some more beans. Just eating some beans. I got some red beans here. Just eating some beans. I got some red beans here. Hi, Dean Miller. I'm just over here eating beans. I've seen it. Two people talking on the same screen. Eating some beans. I got some red beans here. And